So classification. A quick reminder, classification are models where we try to predict a label, which is a category, instead of a real number. So for the fraudulent transactions, we are dealing with classification. Is it a fraudulent transaction or not? In regression, we deal with regular numbers. So we're trying to, for example, predict sales for the next month. That would be a regression problem. So the first thing we look at when we have a trained model and we make predictions with it is that we compare the model's predictions of the label against the real data. And this confusion matrix is one of the easiest, most visual tools that we have to see the results. Let's keep with the fraudulent transactions example. We have two possible results of a transaction. It's fraudulent or it's not fraudulent. Typically, we would say that a fraudulent transaction would be a positive, that it is the event that we are looking out for. So if we have a situation where there is a transaction that in our historical data set is fraudulent and the model correctly predicts that it is fraudulent, we will call that a true positive. It was actually fraudulent and the model managed to correctly predict that it would be fraudulent. So this is what you want, to have true positives. At the same time, if the model is able to take transactions that were not fraudulent, that were normal, and the model predicted correctly that they were not fraudulent, we call that a true negative, which is also what we want. We want our model to give us as many true positives, so correctly predicting a fraud, and as many as possible true negatives, which is correctly predicting that the transaction is normal and that we shouldn't do anything and let the customer be. However, the errors of the model can be classified as either false positives or false negatives. I'm sure you've all heard the term false positive before, especially during COVID, because famously, the tests were optimized to try to be really precise with finding positives. But that means that it will sometimes have false positives. So if you got a positive, like your test said you were infected with COVID, it was very recommended to take another one to see if you got a positive again, because it was really biased towards trying to identify a positive. Like the people who made those tests really didn't want to have someone who really had COVID and then have the test say, like, no, you're good, you don't have COVID. If the test did that, that would be a false negative, because the test would be predicting that you don't have COVID, that you are negative, but it's false because you actually did have COVID. Whereas false positives is that the test said that you have COVID, but it's not true. You didn't actually have it. In the case of fraudulent transactions, a false positive is when you are bothered because your credit card, you're using it, and it says, no, it didn't pass because of a transaction, the bank blocked it. That in that case, you're a victim of a false positive because the model was wrong. You're making a normal transaction and the model flagged it as a positive. So that's a false positive. Okay. Yes, Martin.
No, go ahead, because I think my question was regarding something that it's in this slide, and maybe I made a question later.
Okay, perfect. So based on the fact that any classification prediction can be one of these four outcomes, so if the model says it's a fraud, then it could be a true fraudulent or that the model is wrong. And if the model says it's not fraudulent, then the model can be right if it's really not fraudulent, or the model can be wrong and think that a fraud transaction is actually normal. There are different metrics that we can use, which is very important to talk with data scientists, because depending on your situation, you might want to optimize your model to have the best result in one of these different categories of metrics. So precision is simply the true positives out of all the actual results. Actual results means the real data. So an easier way of looking at it is this. Out of the true positives and false positives, which both mean true positive is when the model is right, and the real transaction is a positive. So the real transaction was fraudulent. A false positive is when the model thinks that the transaction is fraudulent, but it really isn't fraudulent. So when you sum these two together, it gives you all of the times that the model thinks you are facing a fraud transaction. Precision refers to just the true positives. What percentage of the times that the model says, hey, this is a fraud, what percentage of the times that the model is saying, hey, this is a fraud, is the model actually being right? So if there are 1,000 transactions and really 50 are fraudulent, and the model says there are 100 fraudulent, if out of those 100, 50 of them are true, and 50 of them the model was wrong, then the model has a 50% precision. Because out of 100 tries of saying, hey, this is a fraud, it was right half of the time. So when is precision important? Precision is important when you need a high precision, is when it is very costly for your customer or yourself or whatever your business objective to have a model be very trigger happy. Like this is particularly useful when you don't want your model to be saying, hey, everything is a positive. So we'll see some business examples later. But if you have a high precision, it means that your model is very precise. That's why it's called that way. It only says the situation is true when it is really firmly thinking that it's going to be true. It doesn't venture out. It doesn't risk getting false positives. And then recall is kind of the opposite. This one, it's probably, I think, even an interview question for data scientists, like in what scenario do you optimize for recall? This one is the true positives. So when the model is right and the data is actually true, like a true fraudulent transaction, divided by true positives and false negatives. So true positives and false negatives. What do these two have in common? They are on the left side here. So that means true positive is when the model says it's a true fraudulent transaction and it was right. And here, a false negative is when the model says it's not a fraud, but it actually was a fraud. The thing in common here is that in both times, it actually was a fraud. So in here, the model was right about it being a fraud, and in here, it was a fraud, really, but the model was wrong, thinking it wasn't. So what does that mean? If you take these two together, it means the total amount of times that there really are fraudulent transactions. So when you measure just the times that the model is right, you're measuring here what percentage of fraudulent transactions is the model actually able to identify. So if there are 100 fraud transactions and the model was able to identify, let's say, 50 of them, but the other ones, it didn't say anything, then you have a 50% recall. When is recall important? When it's really imperative that this is low. Like when it's very, very costly for you to have a false negative. For example, in fraud transactions, What do you guys think is more important to keep low? You usually have a trade-off. It's hard to have low false positives and at the same time have low false negatives. In a fraud transaction, false positives would mean if you have low, it means that it happens very little, that you are bothering your customers by saying, hey, I'm canceling your transaction because I think this is a fraud. But a very little false negatives means it happens very little that your bank is telling a delinquent that is using your credit card, like, hey, go ahead. This is a normal transaction. Do all you want. And quite obviously, this one is much more important to keep low than this one. This is why you feel like your bank might be bothering you more than you would like. It's because they are optimizing to keep this as low as possible. They don't want evil delinquent robbers to use your credit card and risk a model not detecting it. So in order to keep this as low as possible, they have a trade-off, which is that these ones increase because they make the model more biased towards saying that it's true. By doing that, you're optimizing for recall because you are really making this low. You don't want false negatives to escape from your model. And this is what this is measuring. How many out of the true positives and false negatives, which are the actual fraudulent transactions, how many of the fraudulent transactions the model is detecting? If you have a 90% recall or 99% recall, it means that almost every fraudulent transaction you're able to identify correctly. At the same time, if you have a 99% recall, you're very likely to have a very low precision because while you're identifying all of the true fraudulent transactions, you're probably also making many false positives. You're probably also making a mistake here, like these are all the fraudulent transactions, but you're also sacrificing many normal transactions that you're calling them like, hey, you're a positive, you're a fraud, and they're normal. So finally, accuracy is like the most basic one, but in real life, often you are optimizing for either precision or recall because it's weird to use that false negatives and false positives are equally bothersome to you. Accuracy just means true positives and true negatives divided by the total amount. So it just means what percentage of the time the model is right. And that's it. It doesn't measure anything about the model being biased towards reducing false positives or reducing false negatives. You optimize for accuracy when it doesn't really make a difference to you to minimize false positives or minimizing false negatives.